It is on modern Linux kernel mitigations, and it is by Ray, Veldkamp, and Matt Kurz. So let's please welcome them to the stage.
Hey everyone, my name's Ray and this is Matt. We both work at InfoSect. We're going to be talking about the Linux kernel and some more recent security features. So Russell gave a really great talk yesterday about the history of security in the Linux kernel and how it went from basically having no security to something that looks like a modern OS. So we're going to kind of pick up where he left off and talk about some of the more recent things that have gone into the kernel. So I'm going to start by talking about how a kernel is actually configured and how the distros build it. And I'll talk a bit about how things differ between different distributions and how they build their kernels. And then we're just going to go through a bunch of these mitigations, and we'll try and relate them back to how widespread they are and who's adopted them. So the Linux kernel itself, it's a binary blob which gets decompressed and loaded into memory at boot time. On the file system, it's called VM Linux. And at compile time, that blob is built with all of the functionality that you want to go in, like built into the kernel. So it also supports modular functionality. So it's not practical to just throw everything into your kernel binary. Otherwise, it would be massive. So when you're building your kernel, you can configure with a yes flag if you want something to be built into the blob, or if you want it built as a loadable module, you configure it with the M flag. And so those kernel modules will be located in lib modules, and they'll be KO files. And so at system runtime, they can be loaded or unloaded via modprobe or insmod ironmod. But there's also ways for them to be like automatically, dynamically loaded as well. So the types of things you can configure are things like file systems, networking protocols, even like memory management, but also security mitigations can be turned on or off through this configuration. And so when a distribution is releasing their OS, they'll like often weigh up, it's a trade-off between like the improvement that a security mitigation offers, but also against the runtime performance hit. There might be a really good security mitigation, but if it like slows down the OS a lot, they get a lot of pushback from the community. So they really kind of need to decide what gets turned on and what doesn't. On a running system, the configuration that was used to build the kernel is usually located in boot /config and the uname string, and that'll have like the config of the running kernel and the last few installed kernels. So major Linux distributions, you'd have all heard of them, but they're like Ubuntu, CentOS, Debian, Arch. There's like hundreds of others, like obscure operating systems out there, but they're usually derivatives of one of these OSs. So each distro will essentially fork the kernel. They'll take a version of the upstream kernel, and then they'll build it with their own customized configurations. And most of the OSs, they'll have like long-term support for certain releases. And so what this means is it's like a promise to the users that they'll get like security, like CVE patches, and like security features, and also other like bits of functionality backported for some amount of time. Usually it's 2 years or 5 years, or it can be longer with like paid support through some companies. So an example of how like kernels can kind of differ is like on Ubuntu by default, the SCTP networking protocol is included, whereas on like CentOS and Red Hat, this network protocol isn't there. So you can kind of see that different distributions will have very different attack surfaces. So if you're looking for bugs and you're working them up, usually the attack surface is something you have to consider. So it's not really enough to just say I'm like targeting a specific kernel version. You have to look at the distribution and how it's been configured as well. So an example of like a security mitigation being backported was repbleed, which was last year. I'll talk a bit more about that later. But these repbleed mitigations were backported to Ubuntu 5.15 and CentOS's 5.14 kernels last year. So attack surface considerations. The surface will like vary significantly between Linux distributions. They'll differ in file system types. Things like can an unprivileged user mount a file system, for example, like a loopback device. Network protocols and drivers. There's also like user namespaces, so they let you let an unprivileged user do things like add an interface, send raw packets, that kind of stuff. They can differ in memory allocators, and we'll see later caches can be configured differently across different distros. Things like CPU preemption and read copy update preemption, that can affect, if you've got a bug that depends on a race condition, if you have preemption versus non-preemption, that can result in very different code that needs to be written to trigger the bug. And of course, security mitigations, which we'll be talking about today. The other thing to consider is that not all support is loaded by default. So you have these kernel modules that can be loaded at runtime. So your attack surface depends on what is baked into your kernel binary, but also what's been loaded at a given time. And finally, most of the bigger OS distributions, they have different spins. So there's a server targeted version or a desktop, or even an embedded device version. So these will vary in their attack surface depending on what platform you're targeting. So if you're a distro and you're building your own kernel, or if you're a hacker and you want to make your own kernel, you usually do it through this menu config interface. So if you run make menu config in the root of your kernel source, you'll get this. And it's pretty good. It's characterized by the subsystem. So you just go and tweak your knobs and your features through here, and you'll get a config file out, which you can then run make. So we're going to dive right in and start talking about some of the security features. So Russell mentioned KSLR yesterday, so I'm just going to do a quick recap. But kernel address space layout randomization. So what this will do is randomize the physical and virtual base address of the kernel image in memory. And so what this does is it actually just shifts the binary in memory by a slide. So the symbols will all have a different address at boot time. And so if you want to look at the address of the symbols, if you're root, you can look at /proc/kalsims. So on the image on the left, you can see a kernel is loaded at this base address without KSLR. When KSLR is enabled, it'll be shifted by a constant amount. So the important thing here is because the whole thing is shifted, the offsets between symbols to the base address will be constant. It's just the slide that changes. So if you've got a good bug and you're writing an exploit, this usually requires a KSLR bypass. So if you need to use any functions or know where symbols are, you're going to need to know the base address. So this randomization is done per boot, and it's pretty low entropy. There's actually only 9 bits that change. So it's fairly straightforward to defeat and recover the KSLR slide if you've got a good info leak. So the Linux kernel is huge. Millions of lines of code. There's a history of it leaking data from kernel space to user space, in a lot of subsystems. So if you can leak a function kernel pointer or a symbol address, and because the offset remains the same between reboots, you can determine the base address for the kernel image. So KSLR is good, but it's not that good, and it's been enabled by default on most major distributions for a long time now. So to kind of make things a bit better, they've come up with function granular KSLR. So this was merged upstream a while ago. And basically what it does is it applies a function reordering at boot time, and it's built on top of the existing KSLR implementation. And so what this does is every boot, kernel image is decompressed, and the symbols, the functions are all rearranged every time. So if you get a single info leak, it's not going to allow an attacker to predict or to know every symbol address. So not all regions are reordered by FGKSLR. So some attacks can still use this to construct ROP chains. The patch is emerged upstream, but it hasn't been adopted widely by distros yet. And it results in a small delay in boot time. And there's a high memory requirement for that initial decompression, and there's a runtime hit. So like I mentioned before, distros will weigh up the benefit that this offers versus the performance hit, and they will decide whether or not they're going to turn it on. Config init on alloc default on. So this mitigation came into main kernels last year, I think it was. And so basically all heap allocated memory will be initialized to 0 when it's allocated. So if there are information leak bugs around, you're going to just leak zeros in your data, so you can't use it for defeating things like KSLR, or if you've got sensitive information in your buffers, they'll just be zeroed out. So in the kernel, this affects a lot of network and packet processing code. So the SKB structs are used for network operations, and there's a set of functions for dealing with SKBs. And so this stuff usually dynamically allocates memory on the heap. It does things like allocates headers for packets and payloads for those packets. This particular mitigation just wipes out a lot of those information leak style bugs. This is enabled by default on Ubuntu and has been since the 5 series kernel, but it's not enabled across all distributions. Similarly, we have init stack all zero, so for objects which are allocated on the stack, they'll be initialized to 0, and that includes any padding on the stack as well. So as before, if you've got info leaks, you've got this kind of defense in depth in that your uninitialized data will be zeroed out. This one's not enabled on many distributions that I've seen, likely because of the performance hit. So in Linux, the dmessage command is used for displaying the kernel's message ring buffer. So in the kernel or in kernel modules, if you're print keying or you're logging stuff, that will show up in dmessage. So it also displays boot logs. If you're inserting or removing a kernel module, or crash logs and stack traces, that will all show up in dmessage. So some of this stuff can be pretty sensitive. So you could leak kernel pointers in some of your logs. So there's this config security dmessage restrict option now, and that basically locks access to dmessage down to the root user. This one's also pretty widely adopted. KPTI, so kernel page table isolation. So this was introduced in response to Meltdown a couple of years ago. And basically, it separates the kernel and user space page tables from each other. So the kernel will have access to both sets of page tables, but the user will only be able to access its own pages and a very minimal set of kernel addresses to do that transition between spaces. There's some bypasses out there, and they involve constructing chains to trampoline with this swap restore regs function. That's the function that's used with syscalls normally. So there's bypasses, and with most of these mitigations, they're not silver bullets to locking things down, but they do make the exploit development process a lot more complicated. So this one is enabled by default on most distributions as well. So hardened user copy. If you were at Russell's talk yesterday, he mentioned copy to user and copy from user. So these are the main functions the kernel provides for getting data into the kernel from user space and reading data back out from the kernel to user space. They're generally used a lot in ioctls and device driver read-write operations. So there's a big history of buggy code and bounds checking, which can lead to unintended reads of too much data, or even writes which enable attackers to corrupt sensitive information in the kernel. So this hardened user copy was introduced in the last year, and basically that has some smarts. So if you're dealing with objects that are created on the heap, it'll actually check their size to ensure it's within the size allocated. And it'll also check against page allocations and any overlap with the kernel text segment. So this has eliminated a lot of bug classes, particularly around heap exploitation. And this one's been enabled by default in most distros since last year, I think. I'm going to talk a little bit about kmalloc. So just like user space in kernel space, you can dynamically allocate memory. And the way you do that is by calling kmalloc. And this will get you memory that's virtually and physically contiguous, up to a maximum of about 4 megabytes on x86. When you call kmalloc, you give it a size, and you can also specify flags. So in the majority of cases, you'll use the GFP kernel flag, but there are flags for atomic access and other things. So when you call kmalloc, what you'll do is you'll get an allocation, and depending on the size, it will come from a cache. And there are caches which are organized by the size of the memory chunk that kmalloc is going to return. And these are in power of 2, mostly in power of 2 size increments. In the kernel, like, you can create these caches with the kmem cache create and alloc functions. And these exist for like creating special purpose caches. So for example, struct cred jar is a particularly sensitive structure, so it will have its own cache created. So yeah, objects of the same size, like up to the next power of 2, will get allocated from the same cache, given they're on the same CPU core. So the reason I'm talking about kmalloc is that there's been some movement in how these caches work in the last couple of years. So as of 5.14, kernel memory accounting allocations started using their own set of special kmalloc caches, and these are denoted with this kmalloc CG prefix. The way to configure that in the kernel is with this config memcg kmem flag. So what happens here is if this is enabled, suppose you've got 2 kmallocs for size 128. If one's called with the GFP kernel flag, one's called with the GFP kernel account flag, they'll be allocated from different caches. So if you're doing heap exploitation, you're grooming your heap, and you're doing some spraying, this will impact the choice of object that you can use for that spray. So struct message, for example, is regularly used in heap sprays, but this is now this is allocated from the kmalloc CG caches. So yeah, it will just place further restrictions on use of spray objects. So this might be a bit hard to read, but if you cat proc slab info, you can see there at the top the kmalloc CG caches ordered by their size, and then the regular kmalloc caches. So this is a new feature. It got merged just a couple of weeks ago. It's config random kmalloc caches. When this feature is enabled, multiple copies of slab caches are created as non-mergeable, and a random cache is selected every time you allocate an object, and that selection is based on the address of the caller of kmalloc. So allocations on different code paths and from different subsystems will likely come from different slab caches. So this random selection, it's done based on a per boot random seed, and this is done to prevent using that seed to predict the random allocation order. So this is merged into mainline, but it's not reached distros yet. But from the git commit messages, there's some initial benchmarking, and it looks like the performance impact is quite minimal. So we expect this to land in distros at some point soon. I'm going to talk about a couple freelist mitigations that have come up recently. So heap memory chunks, when they're freed, they get stored in linked lists called the freelist. And a common attack is to overwrite a pointer in the freelist, like the chunks metadata, and get kmalloc to return an arbitrary address. So freelist hardening, it tries to stop this by obfuscating the freelist pointer head, and it XORs it with a secret random value and the address that it's stored at. This is enabled, it's pretty widespread. It's in all the major distros now. We also have freelist randomization. So when a new slab is allocated, allocations from that are sequential, which is good for an attacker to be able to predict. So freelist randomization, it generates a random sequence of indexes. And so the first object will be allocated from a random starting position, and all allocations after that will follow that random sequence. So this aims to complicate heap overflow attacks. There are workarounds for this. It just complicates the exploit development process. So I'm going to talk about structs. So as in user space, when compiled, a struct with multiple members will be contiguous in memory, and their ordering will be as per how the struct is declared in the source code. And the offsets of each of the fields depend on the size of the fields before it. So structs with sensitive information, so things like capability sets, user IDs, or function pointers, they're an attractive target for corruption if an attacker has arbitrary write capability. So there's a history with struct cred and a bunch of other task structs corrupting fields in this for the purpose of privilege escalation. So given you know the offset of the sensitive field in the struct, corrupting that could give you increased privileges. So they came up with this GCC plugin ranstruct mitigation. And what this does is it allows a developer to annotate a structure so that the layout of that struct will be randomized at compile time. So when this is enabled, structs with like only function pointers in them, they're automatically randomized. And this is designed to protect structures with sensitive fields, like I mentioned on the last slide. So this isn't amazing because this randomization is done at compile time. So it'll impact exploit development complexity, because as an attacker, you'll need to get the kernel image, figure out the offsets, and then kind of like maintain that across versions. So it's not super effective for the main distributions where the kernel binaries are used by millions of people, but it's likely more useful for targets who don't publish their kernel builds. So this one hasn't been widely adopted yet. And you can hopefully see here, this is the implementation of struct cred as of a few months ago. And the definition of the struct has an annotation down the bottom in red, randomized layout. So that marks it as a candidate for this randomization at compile time. I'm going to talk quickly about rep bleed. I'm not going to go into too many details, but in 2022, rep bleed happened. It's a speculative execution attack. This one exploited return instructions and specifically retpoline, which was developed as a mitigation for the Spectre v2 issues. So a proof of concept was demonstrated against AMD and Intel CPUs, and they were able to leak sensitive things like Etsy shadow and keyrings and stuff like that. So there was a lot of work into building mitigations for rep bleed. There were like thousands of lines of code, and they were merged late last year, and they were quickly backported to distro kernels all the way back to the 4.0 series of kernels. So we'll take a look at one of these because it affects current attack techniques. So config rethunk. So GCC was updated to now include a feature. It lets you specify an external return thunk. And what this does is basically in functions, they have return statements. They'll replace these with a jump to this return thunk. So this feature was added specifically for this rep bleed mitigation development in the kernel. So yeah, ret instructions are replaced with a jump to the address of that return thunk. So now the surface of the return is like located entirely in a single function. So the reason this is a bit painful is that it impacts kernel ROP chain development for targets which enable this mitigation. And yeah, this was introduced upstream in the 6 series of the kernel late last year, and it was quickly backported to Ubuntu CentOS, all the main distro kernels. So I took a look at the number of ROP gadgets in the kernel before this was backported, and the ROP gadgets after. And you can see in this 5.15.25, there were about 100,000 ROP gadgets ending in a ret. So you want your gadgets to end in a ret when you're building a chain. And then in the kernel after this mitigation was implemented, there were only 3,000. So there's significantly less gadgets in the newer kernel, or so it seemed. This is really hard to see, but a lot of these gadgets, this is just output from like standard ROP gadget tool. A lot of these gadgets end in a jump to this address, which ends in 2480. So if you look at proc KLSIMs, we can see that this address, which comes up a lot, it actually corresponds to a symbol called x86 return thunk. So if you disassemble this symbol, you can actually see the disassembly is just a single ret and an int3. So provided you know this symbol, if you have the kernel image, you can look at system.map or whatever. You can still construct krop chains. You just have to modify your ROP gadget output to use this jump to the return thunk. So I'm going to hand over to Matt now. He's going to talk a bit more about kernel modules.
Hello. For the second half of the talk, I'm going to take a slightly different tack, and what I'm going to do is we're going to look at some historic attacks against the kernel, and then the mitigations that have been added in to prevent them. And I'm going to start by expanding on kernel modules. So Ray spoke a little bit about kernel modules before, and what they really allow you to do is add functionality to a running kernel. And like Ray said, the reason why these are so important is they allow distributions to ship kernels that support the general use case, and then anyone who requires something in extension of that. So for example, if you want to run non-standard networking like multipath TCP or SCTP, or you have a graphics chipset that requires a special driver, they can ship that as a kernel module so that, say for example, I have an AMD graphics card, I don't have to have the NVIDIA code in my kernel. Kernel modules can be loaded into a kernel in a variety of ways. You have the standard administrative tools that Ray mentioned, so that's modprobe, insmod. And to use these tools, you have to have the capsys module capability. Otherwise, you will get a permission denied error. Separately to those, there are also two syscalls, init module and finit module, that can be used to load up a kernel module as well. And they also require that capability too. The final option is it is possible to have the kernel automatically load modules for you, subject to some constraints. And we'll go through an example of that later. So kernel modules provide an attractive, I guess, mechanism for an attacker because they allow a root user to dynamically insert functionality into a running kernel. So as part of, say, like a post-exploitation chain, they provide an attacker quite a lot of functionality to be able to bootstrap things like a backdoor or a rootkit. And the general way something like this may occur is an attacker gets a foothold on a system with user privileges, and then they can do a privilege escalation to root. And at that point, what they can start doing is dropping kernel modules and loading them into the kernel. And the reason why they might want to do something like that is to do something like process stealthing, that is like hide their activities from legitimate tools, or hooking net filter to look at packets, et cetera, et cetera. Any attacker is going to use the same kind of techniques to do this that I mentioned on the previous slide. So you've got modprobe or insmod. They're probably more likely to use init module or finit module, as it's easier to do a fileless attack using these two. Or if they really wanted to, they could use the kernel autoload functionality, but it would not be pretty. So to defeat these kinds of attacks, something called module signing enforcement was introduced. And module signing enforcement is simply just the application of code signing to kernel modules. There are two configuration options that turn this on. The first one is sort of really just a halfway measure, and it's config module sig. So what it will do is it will say, OK, well, I'm going to allow the load of this unsigned kernel module, but I'm going to log about it in the kernel message buffer, and I'm going to taint the kernel so that there is a record that an unsigned module has been loaded. The second one is basically full mitigation. And what it does is it just straight up prohibits the load of any unsigned module. Now, when we talk about code signing, obviously we have certificates and a root of trust as well, and these things are no different. So module signing enforcement has a chain of trust, and it will only load kernel modules that are signed by trusted keys. These keys get stored in this built-in trusted keys keyring in the kernel, and they're usually baked into the kernel when it's built. So all of the distributions that I guess distribute these kernels, they will be baking their keys in such that when they ship their modules to you as well, they will actually be loaded. It is possible to add new keys to this keyring. So say, for example, you want to ship your own modules to systems that you control. Obviously, you can't sign with the distribution keys because you won't have the private key for them. So what you can do is you can add a key in, but only if you can have your key signed by a key that's already in there. So that's probably not actually going to work unless you build the kernel as well. Modules, on the other hand, are signed at build time, but really what that means is they're signed at some point prior to load. The next area I'm going to talk about is something called k-pointer restrict. So historically, and Ray mentioned this as well, the Linux kernel has leaked kernel pointers through multiple interfaces. So we're talking procfs, sysfs, dmessage, etc. It's usually in the past been possible to say cat a particular file in proc and get the kernel address for a symbol you care about. Ditto for sysfs and ditto for dmessage. And so when KSLR was introduced, this was a really big problem because it leads to very trivial KSLR bypasses in the way that Ray mentioned earlier. So k-pointer restrict was introduced in circa 2010. So this is an older mitigation to mitigate this. And it consists of two components. The first is a procfs pseudo file called k-pointer restrict. And it holds a tri-state. So it's either 0, 1, or 2. And depending on the value of that controls what the kernel does when it is requested to print a kernel pointer. The second aspect of this is a printk format specifier. So if you're not familiar with printk is to the kernel what printf is to user space. It's simply a way to print a formatted piece of data to some endpoint. So it could be procfs, it could be sysfs, it could be the kernel message log. And so a special format specifier was added in, which is %p capital K. And that was for kernel developers to use when they wanted to print pointers. And so what happens is when that is used in the kernel, when that's executed, what will happen is the kernel will consult this K pointer restrict value. And if it's set to 0, the pointer gets hashed. Unless, of course, the no hash pointers kernel argument is enabled, which it will never be on any distro you'll ever see. K pointer restrict equals 1. The pointer will be printed as all zeros unless the reading user has the cap syslog capability. And if K pointer restrict equals 2, the pointer is going to be printed as all zeros regardless of the privilege of the reading user. So root could be trying to read these things and it would still show 0, which is a really good improvement over what was there, especially bolstering the improvement of KSLR. Any modern distribution you see is going to have K pointer restrict set to 2. There's really no real reason why it would be either of the other two. Generally speaking, we're moving into an age where nothing in user space should be able to leak a kernel pointer. So 2 is probably the setting that you'd really like there. The next area that I'd like to talk about are user mode helpers. Now, in normal operation, there are a variety of scenarios where the kernel needs assistance from user space to accomplish some operation. These are things like loading modules, core dumping, so if a process hits an error condition and needs to core dump, bin format handlers, etc. And the kernel refers to these binaries on disk that assist it with these processes as user mode helpers. There's a whole heap of infrastructure in the kernel for these things to be called and invoked, but the really salient point that is going to, I guess, hold true through the next few slides is that these user mode helpers end up being run as root with full capabilities. And so when I talk about capabilities, I don't know if we've mentioned it in this slide, I'm talking about cap syslog, like on that previous slide. It's basically fine-grained ability to perform any action you'd like. So over the course of since it's been in the kernel, user mode helpers have been really attractive targets for attackers. And the reason is because it's possible to get these things running as root with a full capability set. And we'll talk about an example of how this happens and how it is attacked. And you'll see this in CTF write-ups, you'll see it in CVE write-ups as well. UMH gets targeted quite a lot because it provides a really, really cool primitive to attackers. But for now, we're going to consider a specific example that occurs when a user space process creates a socket. Now, I spoke earlier on about how it is possible to have the kernel automatically load kernel modules for you. And this is that case, and this is one of those cases where that can happen. So if you've never done any network programming before, a socket is simply a mechanism through which a user space process can communicate with a network. The C library call for creating a socket is simply there. It's socket. It takes 3 arguments, but the one we really care about is this domain argument. Now, domain can be one of many things. It can be AF-INET if you want an IPv4 socket. It can be AF-INET6 if you want an IPv6 socket. But it can also be, I guess, less common. So it can be things like AF-CAN if you want to talk on a CAN network. And it can be AF-Bluetooth if you'd like to talk Bluetooth. But the thing is, there's such a multitude of these domains. And a distribution kernel that you may have may not support all of them. So Ray spoke about earlier that when menu config is done and these kernels are configured, you can opt to have functionality compiled into the kernel if you specify Y. You can have it shipped as a module if you specify M. And you can just not support it if you specify N. And so this hits a problem when we try to create a socket. We might say, hey, look, I'd like you to create me a Bluetooth socket. And the kernel needs to figure out whether it can support a Bluetooth socket. And the cases we have are the functionality is compiled into the kernel. the functionality is sitting in a module on disk, or it doesn't support it. So how the kernel figures this out is it first looks through the ones that are compiled into the kernel, and if it finds it, that's great. It basically palms it off to that. If it's not, it needs to figure out whether there's a module sitting on disk that can support this particular domain. And so if it needs to go out and look on disk, it invokes modprobe to do that. And so the next problem we have is the kernel doesn't know where modprobe is on disk. And so what it has is this global variable called modprobe path. And it purely exists to hold the path to the modprobe binary on disk. This modprobe path variable is controllable through the modprobe pseudo file in proxys kernel. And when the kernel wishes to invoke modprobe, it basically just runs whatever this global variable is set to. So it's usually set to something like /sbin/modprobe. However, if you as an attacker were to say change it to /temp/bad.sh, it would run that as root instead. And that's essentially the attack that usually gets levied against user mode helpers. So to elaborate, if we want to attack this, and we're going to assume we are an attacker and we have a sufficient primitive in the kernel such that we can overwrite what this modprobe path variable is. So for that to happen, we're talking of something like a write what where we can write a value we control to a location we control. And what we're going to do is we're going to overwrite modprobe path to point at something else we can control. So on the previous slide, I threw out an example of /temp/bad.sh. It can really be anything as long as the kernel can run it. So you need it to be like, if it's a shell script, you want it to have that shebang line in the top. So hashbang, bin bash, and then whatever you want in it. It can be an elf executable. As long as it has a registered bin format handler and it's marked executable if it needs to be, you're good to go. The next thing we're going to do is we're going to cause the kernel autoload function, like module autoload functionality to be invoked. And we're going to use this socket example that we used before. So I'm going to go in and I'm going to say, hey, I want to create a socket and I want to talk AFCAN, for example. But the real trick is here, I have to pick something that isn't compiled into the kernel. There's a ton of ways you can figure out what's compiled in and what's not at runtime, and I won't go into them, but just pick something exotic or something that doesn't exist. And what will happen is the kernel will go, well, I don't support this. Let's invoke modprobe. And by modprobe, I really mean whatever modprobe path points at. And then what happens is our /temp/bad.sh will get executed, and it will get executed as root with a full capability set. So what that means is basically we can do absolutely anything we would like at that point, with the caveat that we don't have interactive access. So you could point it at bin bash, but you'd never be able to give it input. So one option that is available to you would be to do something like copy bash to temp and then mark it as setuid root. And then once the modprobe fails, you can just go in and execute it and you would have a root shell. If you wanted to clean up after that, you could just reset modprobe path via proxys kernel modprobe. For those of you that care about the details, this is a really cool attack because it can be done from interrupt context, which is really, really nice. So I said up front, this gets used a lot. And so there are mitigations that are designed to prevent it. And that is the config static user mode helper configuration option. And what that does is it basically says all of these user mode helper calls have to go through a single binary. And that binary is specified by this configuration option, user mode helper path. Now, config static user mode helper is unlikely to be enabled on any distribution you'll see today because it requires user space support. It requires that the distribution ship a binary that can do modprobe, but it can also be a registered bin format handler. It can also be a core dumper. And so whilst that support is actively being worked on, it's unlikely to be enabled today, but give it 2 years, 3 years, and it's probably going to be a thing. The next area I'd like to talk about are actually kernel process stacks, but to do so, I want to take a quick detour through vmalloc. And so Ray spoke about kmalloc earlier, which is really the kernel's general purpose allocator. It's going to be the first thing you reach for if you want to allocate memory in a kernel context. but it is limited in the fact that it can really only allocate you about 4 megabytes of memory. And the reason why is because it gives you physically contiguous memory. And 4 megabytes of physically contiguous pages on any kind of running system with memory fragmentation is going to be a tough ask. So if the kernel needs larger allocations than this, for example, it wants to load up a bigger kernel module, or kernel process stacks, or graphics buffers, or it doesn't require the physically contiguous memory, it can use this separate allocator called vmalloc. And so unlike kmalloc, vmalloc allocations aren't physically contiguous. That is, the pages aren't necessarily sequential in memory. It obviously comes with the caveat that you can't use APIs that expect physically contiguous allocations, such as multi-page DMA. But the really cool thing is that vmalloc will very nicely give you like a guard page after your allocation, which gives you some sort of base level of security against linear overflows. So how does vmalloc actually allocate memory? So what it does is it will go through memory and it'll say, give me basically any page you have. I don't care if they're contiguous. If they're free, I want them. And so what will happen is it will then take those pages and then it changes the kernel page tables to make them virtually contiguous in memory. And I'm not sure how visible that diagram is. However, on the left, we have our kernel virtual address space. And we're going to assume that we have asked vmalloc to give us 3 pages worth of memory. On the right-hand side of that image, yes, on the right-hand side, we have a very basic view of physical memory. So we're assuming that we have 5 pages of memory, A through E. Page B and D is already allocated off to somewhere else, and we've asked for 3 pages. So what it's going to do is it's going to go give me A, C, and E, which are their 3 free pages in our example up there. You can note they're not physically contiguous. You can see they're quite actually sparse. They're separated in physical memory. But what vmalloc will do is it's going to take them and it's going to stitch the page tables together such that they appear virtually contiguous in the address space. I mentioned before, there's a very nice security property in which vmalloc will give you a guard page at the end of the allocation. So if there's a buffer in that allocation that as an attacker you can write straight off the end of, all the way off the end of the allocation, you will hit a guard page and it will basically stop the process that does that. I don't have an example of an attack against vmalloc, but I will say that as an attacker, if you are trying to, groom vmalloc into an advantageous layout, it is possible. I'll briefly cover these. So vmalloc will give you back the lowest virtual address in the vmalloc range that can hold the allocation, which makes them semi-predictable. That means you can spray vmalloc allocations to get an advantageous layout. But the really big caveat in doing this is that when a vmalloc allocation is freed, it's not truly freed. So when setting these things up, the page tables have to be modified, which is the same when the allocations are freed. And that's a really costly operation because you end up changing the page tables, you end up flushing the TLBs, and that's quite resource intensive. So as an optimization against having to do that every time, what will happen is vmalloc, when an allocation is freed, will hold on to it, and then when it builds up enough that are freed, it will purge them all. So what that means is refilling a hole to, exploit a user after free isn't immediately obvious because it will hold and purge these allocations at different times. If this is something you need to do, there are public materials out there. You can Google them. For example, here's one from Project Zero that had to do a similar thing. So that moves us on to kernel process stacks. So every process that runs in user space has a corresponding kernel stack. And this stack gets used when the process transitions to kernel mode. And that usually happens when that process does a system call. Kernel process stacks actually get allocated in vmalloc space when the process is created, as long as this particular configuration option is set. And any distribution that you run today is going to have that variable set. It actually gives you quite a bit of security from having your kernel process stacks in vmalloc. Similarly to user space, buffers on a kernel process stack can also be overflowed. So I guess you would refer to this as a kernel buffer stack overflow. Obviously, because the stack will be vmalloced, it is bracketed by guard pages, which gives us some protection, but there's also a static canary that's placed at the top of the stack. This canary is not there for security because it is a fixed value. It's mainly there for debugging. However, these mitigations, these guard page mitigations don't protect against things like out-of-bounds writes. So if you can write from some offset from a location on your kernel process stack, and you can skip that guard page altogether, there's no protection there. So that specific scenario, along with some others, resulted in these mitigations called randomized k-stack offset. There are two of them. There's config randomized k-stack offset, which is like that halfway measure that I spoke about. It compiles the code in and then consults a kernel boot parameter as to whether to turn it on. The second one is randomized k-stack offset default, and what that does is it turns it all the way on. And how this mitigation works is it aims to defeat attacks that require kernel stack determinism. So attacks that require a particular buffer to be this far from a particular buffer. And how it works is when the process transitions to kernel execution via the syscall, a random offset is added to that kernel process stack. And that offset changes each transition. And this adds about 5 bits of entropy on x86-64. So with no mitigations, it looks a little bit like this. Right down the bottom there, it's probably really hard to see, I'm sorry. But the first thing that happens is user space registers get pushed to the bottom of the stack, and then the stack continues from there. What this means to an attacker is that the layout is deterministic, and the offset to the end or the beginning of the vmalloc allocation is known. And what that really also means is the offset to other objects in vmalloc space is also known. So that means doing those out-of-bounds writes and reads becomes way easier. The mitigation here is to add that random padding down the bottom, which once again, I'm really sorry, is probably hard to see. And so what it will do is it will allocate this random size that it never actually uses, and then which moves the kernel stack around. And so what that means is there's no longer that deterministic way to figure out how far from the end of the stack you are, how far you are from adjacent objects, which really helps out quite a bit in defeating these types of attacks that require kernel stack determinism. You will likely find this turned on any current distro because it is quite effective. The next thing we'll talk about is reference counting. So if you've never heard of it before, reference counting is a very common pattern in software engineering to control the lifetime of allocated objects. And the real question that it answers is, if I have an object that is being accessed concurrently by multiple CPUs that was dynamically allocated, when can I actually free it? Because we don't want to free it when something's still using it, because that leads to vulnerabilities or crashes. And it actually ends up being quite a tricky problem. And reference counting solves that. And it works quite simply. So as a consumer of an object, if it wants to use that particular object, it does something called it gets a reference. And all that really does is atomically increments a count. When it's done with the object, it puts the reference, which decrements the count. And when the reference count equals 0, the object can be freed. So reference counting is a really big deal across the kernel because it is used almost everywhere. And it's really used in a lot of things that have security relevance. So things like struct file, which is the object in the kernel that represents an open file, cred for credentials, skbuff, etc. Like I said, it's historically implemented as an atomic T. And really all that is an indication to the programmer that they need to use atomic safe functions to access it. Because it can be, this count can be incremented and decremented by multiple CPUs concurrently. Historically, reference counts have been a source of bugs. And it is really, really tricky to get this right sometimes. And so incorrect reference counting would, in my opinion, be the biggest case where this arises. And so things like, if I have a dynamically allocated object that has a pointer to reference counted object and I duplicate that somewhere else and don't grab a reference to the reference counted object, that's a bug. And they tend to lead to use after freeze. And if you think about how complex the kernel can be, these things arise quite a lot. Reference counts also present an interesting target for attackers if the attacker has the correct primitive. So if I, as an attacker, have the ability to overwrite or influence the reference count of another object, what I can do is I can make that count lower than it actually is. And what that allows me to do is synthesize a use after free that I could then possibly exploit. To mitigate these sorts of attacks, the refcount T type was added into the kernel. And the real mitigation that comes with this is the functions that you use surrounding this type. And how the mitigation works is basically they will automatically detect when the reference count is in a bad state. And so a bad state may be something like, I as a consumer am asking to get a reference to an object, but that reference count is already 0. That's a use after free. Something else might be, I'd like to get a reference to the object, however, its reference count is at the maximum value that an integer can hold. All of these things are erroneous. And so when the refcount infrastructure detects something like this, it does something called saturates the ref count. And what it does is it basically sets it to a static value. And once it hits that value, nothing else will be allowed to happen on that object. So it won't be freed, but you can't get a reference to it either. It does mean that that memory will be leaked, and by leaked I don't mean to user space, I just mean like it won't be able to be used by the allocator anymore. But it tends to be a pretty good mitigation, and it's pretty effective at mitigating these scenarios where you could overflow a ref count or underflow a ref count. It was designed to and is quite effective at stopping those things. So refcount T is in use in quite a lot of areas of the kernel. However, it's not kind of wholesale across the kernel. So there are still quite a few security relevant areas that haven't been converted across. So it's worth still knowing that you can play games with reference counts as a general term rather than these ref count T's if you have the appropriate primitive. And that's us. Thank you.
Thanks.
Great talk. Do we have any questions in the audience? Just raise your hands. Do I see any in the audience?
Cool.
One over on the top, up there on the left.
Hey guys, thanks. Great talk. Just wondering if you guys had any insights on how what you've talked about today impacts things like security context and RHEL.
Sorry, can I get that last bit again?
So how what you've talked about, like the kernel mitigations you've talked about today, how that sort of factors into the overall hardening of security contexts and how that's used in operating systems like RHEL.
Yeah, I mean, basically security hardening for a distribution, it all comes down to risk profile, right? So as an end user, you figure out what your risk profile is. So if I'm storing a lot of sensitive material on my laptop, I might want a higher security profile and I might want to turn on more of these. One of the things we see with distributions is that they cater to different things and they still have to be usable as well. So each distribution tends to take a different approach. So if we think of all of these mitigations as kind of like a grab bag of things that we could use to enhance security, possibly at the cost of usability, they all kind of pick and choose different ones to achieve their goals. Do you want to jump in? Does that roughly answer your question? Cool.
Are there any other questions in the audience? One in the middle at the front here.
how well adopted is the signing of the kernel module so far? If I turn it on, is it going to break all my drivers?
I would say piecemeal, so I wouldn't expect to see it on your standard distro.
No.
And the reason why I wouldn't expect to see it on is a ton of people still have NVIDIA drivers and NVIDIA ship them. So that's going to be the biggest problem you see. Generally speaking, yeah, I would say it's probably not on. If you're running RHEL, it might be on. A lot more of your enterprisey type ones turn it on, but your Ubuntu doesn't have it. And I don't think Fedora has it either.
Any other questions? Just to yep, just there.
Are you seeing much of a difference between desktop distributions and server distributions in that regard? Is there like a divide between security options that are enabled?
Not so much security, but all the other stuff I talked about, like networking protocols, file system types, that stuff can vary wildly between the two. Yeah.
And maybe one last question, if there is any in the audience.
I've got one, Silvio again. Hello?
Yep.
So, hello, over here.
Hi.
So, for us who aren't kernel developers, how is, for end users, how do we keep track of what's being introduced into the mainline kernel? How do you recommend security practitioners, especially blue teamers, keep on top of kernel functionality?
That's an excellent question. So generally speaking, a lot of these things will transparently filter through to end users through the distributions. I guess if you're doing blue teaming for an organization that has the budget for it, a lot of them will actually be using distributions from vendors that have security teams that do this for you. So RHEL has security teams, Canonical has security teams. They kind of do that in a way. So I guess via the transitive property, that's one way it could happen.
If you're on a long-term support kernel, so like with Ubuntu, there'll be detailed change logs whenever they have a 6-month release cycle, and so any big things like the stuff we've talked about today, when that lands, there'll usually be blogs and write-ups and change logs about it. So you don't need to dig into the kernel binary or anything like that.
Failing that, if you as an individual would prefer to stay on top of it, the kernel mailing list is probably the good one, the security hardening mail lists. And then keeping up with those, and then you can kind of turn on those configuration options as you see fit. But obviously that comes with the side effect of having to maintain your own kernels.
Yeah, so I just, we went through the whole meltdown saga as blue team responding and, you know, the actually responding to it, but not knowing what's going under the hood. So thank you very much for that.
No worries.
We have some speaker gifts for you backstage, but let's thank Ray and Matt one last time.